Yeah, thank you. So indeed, that's a little bit what I consider to be the goal of this lecture series, is I would like to offer, of course, next week there's a conference maybe on Kudla program, and then specifically the p-adic Kudla program. Personally, I'm not exactly sure what the p-adic Kudla program is, but I'd like to offer you in this lecture series through a couple of instances that one might consider a p-adic Kudla program, a sort of first preliminary exploration of what this program might entail. And so what I'll do is I will focus it on one specific example with a sort of independent arithmetic application, and I will build the lecture series around the work of Gross and Zagier, and also my own work with Henri Darmon, RM singular moduli. So I'll explain a little bit this theory, and then as we go along, we will sort of explore what the p-adic Kudla program has to say about these quantities. So that's a little bit my goal. Today will be quite relaxed. I think what I would like to do is I would like to sketch the context of the work of Gross and Zagier. And so I'll spend a bit of time first talking about the classical, the Archimedean work of Gross and Zagier. And in order to do that, I would like to tell you a little bit about what was going on at that time. And so I'd like to start really with quantities that were studied by the classical German school, notably people like Kronecker. And so the starting point for today's lecture, is it okay if I write on this one first? It's all right? Okay. All right, so the starting point will be special values at points that belong to the upper half plane and that are imaginary quadratic. And I will do this particularly focused on two special functions today, which is the J function, which we all know and love, where delta of Q is the usual Ramanujan tau series. So this will be in the usual variable Q, which is e to the 2 pi I tau. And if you expand this as a Q series, what's important for today's lecture is that this is a Q series defined over Z. Okay. So most of you will be familiar with this. Sorry? Yeah, at some point as a sort of circus act, I memorized this one and I still remember, unfortunately. So now I can't resist always writing it down.
Gross and Zagier to the spirit.
Indeed, exactly. That's a little bit what we're going for today. So Zagier would know the next one too, I'm sure. But I do not. No. Okay, so the second set of functions sorry, that's not really legible. That's an H sub gamma.
Actually, is it visible in the back?
Is that an issue of positioning or font size?
Font size.
Font size, okay. Good. That's the story of my life. So I will not be offended if you remind me a lot to write larger. H of gamma. Larger is usually uglier, right? But hopefully you forgive me. So this H of gamma, let me define it for you. So it'll also be obtained from the Ramanujan delta series. And I will hit it with the usual weight 12 action of matrices gamma as a Q series, and then divide out by delta. Yeah? Where gamma will belong to a set that I'll call MP. And this set will be the union, let me call it J actually, of these matrices as well as this one. So the usual coset representatives for gamma 0 of p inside of SL2ZP. Yeah? So those are the functions that we will study. Yeah, where, just for completeness, this is the Ramanujan delta function. Okay, so the first part of today's talk will be about the first two quantities. So in classical CM theory, you have this sort of holy trinity of invariants with various levels of sophistication, which all interrelate. And so I'll focus first, in the first half of today's talk, on the classical theory of the first two, and discuss the theory of modular polynomials. Yeah? So, for simplicity, P will be a prime, which it already was here. And the goal is to define two particular modular polynomials which I'll call phi p of x and y and epsilon p of x and y, which will be used to study singular moduli, which is the name I give to the CM values of the first function, and elliptic units, which is the name I give to the CM values of the second set of functions. Okay? All right. So first, very classical result. There's a unique polynomial, phi p x y, so it's in two variables, and it has integer coefficients. And it's characterized by the fact that if I take this polynomial, phi p x of y, and for y I substitute the function j, then I get a polynomial of x with coefficients in, I guess, polynomials in j. And I want that this factors as follows. Okay. Now this polynomial satisfies three properties, which most of you will have seen before. So the first is that it's symmetric. So if I switch x and y, I get the same polynomial. The second is that if I restrict it to the diagonal, so I do phi p xx, then I get a polynomial with integer coefficients whose leading coefficient is just plus or minus 1. And finally, a result that's known as Kroneker's congruence. If I take this modular polynomial and I reduce it mod p, I can actually tell you straight away what it is. It's this polynomial, which is sort of a first flavor of what the reduction of x naught of p looks like at the bad prime. Okay, let's see. Nope. I remember when you prepare a lecture at Lumini, you always have to build in a couple of extra minutes to work the technology. So far, so good. Okay. Now we'll do the second one. Oh, actually, I better lower the first one too, right? Okay. Is that visible? It's enough? It's not optimal. Okay. It's better? No? Okay. Okay. All right, so many of you will have proved this before. Let me just give you the key ideas. If you haven't seen it before, work through it. It's not very complicated, but I'll give you sort of two key ideas, and I won't give all of the bullet points. But so what you can do is, oh, now I put the board all the way up there. That polynomial, the product, gamma in MP x minus j gamma tau, let's call that p of x. That polynomial. It's too late to write it next to it, but let's call it that. So the coefficient of this p of x, they have three properties. So they're holomorphic on the upper half plane. They're also invariant under SL2Z. And that's because they're elementary symmetric polynomials of these translates of j by this set of coset representatives MP. So if you hit it with SL2Z, you will just rearrange those functions and you'll end up with the same expression. So we get that they're also invariant under the group SL2Z. And finally, if you check at infinity, you will find that there's an integer. It's a power series in Q. It's also meromorphic at infinity. And these three facts together already imply for you that the coefficients of this p of x must be a polynomial in J. So these are square brackets. That's important. Okay, that's not quite enough yet, because I claimed it's a polynomial with integer coefficients, but that's also not super difficult. Because note that if I make these substitutions, gamma of tau, the gammas are explicitly on the board, you will get expressions of the following form. So you'll get 2 pi I, and then you get tau plus j over p. And this, of course, I can write as zeta p to the jth times q to the 1 over p. That's what that is. So another thing we can say about the coefficients as Q series this time is that they're in Z zeta P Q. Maybe I have to invert Q as well. But they're also Galois invariant. For the action of the Galois group of Q zeta P over Q. Because if I let that act, it acts on these kind of norms. By just swapping them around, and again, we have elementary symmetric polynomials, so that shows that it's invariant under this Galois action. And we get that really this thing must be a polynomial in J with integer coefficients. Okay? All right. Now, that doesn't prove all the properties yet. I'll leave the others for you. These are already the key ideas. The most notable one for us is the second one. The fact that, of course, if you restricted the diagonal, you get leading coefficient plus or minus 1. You can check that essentially using the same idea here. So you can check that the leading coefficient must be a root of unity, first of all. So you get no more complicated expressions than just powers of this zeta p. And again, it's invariant under Galois. So it better be a root of unity in Z, and therefore it's plus or minus 1. Okay. All right, so classically, I mean, you may have heard of these modular polynomials as being kind of beasts, and that's a little bit the point that I want to get across today. And that'll be what contrasts it with these elliptic units that will come later on. So the examples, there's very few examples that I can tell you. In fact, I won't tell you a single one. There will be notes. In fact, sorry, I should say this. So some of what I'm saying, maybe not so much in the end, but there is some overlap with a lecture series that I did at PCMI in 2022, for which there are lecture notes which you can find on my webpage. I think it was linked to also in the description of this course. So you can follow along there for much of this. There will also be notes, but they will focus sort of on the complementary aspects. But I haven't written the notes yet, so that doesn't help you much. All right, so one classical example, which is so old that it's unclear who knew it, but Jacobi already knew this, and certainly Kronecker and people of that era, is that the second modular polynomial, I've given you the defining property so you can imagine computing it yourself, It has lots of coefficients, and they're very, very large, and I'm just going to tell you the constant one. Yeah? So it'll end in 2 to the 12 times 3 to the 9 times 5 to the 9. Okay? That's the factorization. So quite a large number. And the dots are also very large. Okay, phi 3. Yeah, so this part is quite predictable. You can think about why it will always start off like this. Then I'm not telling you about the middle ones. And then we get 2 to the 45 times 3 cubed times 5 to the 9. X plus y. Now this one already, so this was computed by someone named Smith in 1878. Okay. Now the next one, phi 5, which will start off with the 6th powers. And then the constant term is 2 to the 90th, 3 to the 18, 5 cubed, 11 to the 9th. And this one was computed by Burrick in 1916. Now I'll stop here because the next one, the 7th one, was only computed in 1975. So just to give you some idea of how humongous these things are, I'm only telling you the constant term, but I've eliminated all this mess. If I would show you the whole polynomial, the lecture would be over because I would be writing the whole time numbers on the board. So they're really gargantuan, and that's sort of something we have to keep in mind. They have very large coefficients, but the factorizations look very rich, and that's something I would like to come back to later on. So so 1975, so you probably know people who lived in the era where these were the only examples available of modular polynomials. Okay. I might as well mention the name also. Okay. All right. Now, already from these very simple properties that we established, it follows that singular moduli are algebraic integers. So that in and of itself is not a terribly deep fact once you know about all of these structures. So let's talk about why this is true. The values of j tau at tau imaginary quadratic are algebraic integers. And so, just for future reference, I've already used the name several times. This phrase will be referred to as singular moduli. So the values of the j function at imaginary quadratic arguments. Okay. How do we see this? Well, let's suppose, and so now I will sort of take the freedom to switch between the viewpoint of the j function being a function of the upper half plane or a function on lattices. So suppose that O is any imaginary quadratic order and I will take a prime P which appeared in my story from before, but I'm free to choose it, and I will choose it in such a way that the prime P splits, and it doesn't just split, it splits into principal primes. Of course, in general, O could have some class number, and if it splits, then it's not necessarily split into a product of two principal ideals. But, of course, class field theory will already imply that such a choice is always possible, but in fact, you need a lot less than class field theory to justify that you can make such a choice. But nowadays, we know it's a positive density choice. Now, suppose we're in this situation, which we can put ourselves in. Then, if I take any ideal A, fractional ideal in this ring O, and if O is not maximal, it's not Dedekind, then it's better to take A just to be an invertible ideal. So then this inclusion here has index P. Okay. And if it has index P, that means that on the lattice, I can go from the lattice A to the lattice P times A by picking a basis and multiplying it by one of these elements in the set MP. So these two guys will show up in my modular polynomial from before. So the key chain of equalities here is that now if I take, for this choice of P, phi P, and I evaluate it at J of A and J of A, so this I know is a polynomial with integer coefficients and leading term plus or minus 1. Then, well, because this is principal, I know that that doesn't really affect this value. And therefore, I get that this is equal to 0. So we conclude that this is an algebraic integer. Now, of course, it's not very informative yet because I haven't told you in what field it lives, etc. So there's still a lot of fine-tuning to be done. But we see that we found algebraic numbers, in fact, algebraic integers, relatively quickly. Okay, so in this classical era, these kinds of arguments were quite well known. But there was also, in order to fine-tune the information and figure out in what fields they exist, this other modular polynomial, epsilon of P, came up, which accounts for the elliptic units in this story. And so let's sort of repeat what we did, but switch from using the J function to these H functions, just this collection of P plus 1 functions that we saw before. And the result is very similar to what we had before. So there's a unique epsilon P, x comma y, with coefficients in z, x, y, such that if I take this epsilon P, and instead of the variable y, I now plug in the J function again, then I get the following polynomial. X minus H gamma, where gamma runs over all of the matrices in MP. Okay. Furthermore, the following properties hold in this polynomial. If I take this epsilon, and instead of the x variable, I plug in 0. And the y variable I leave. Then actually that's not a very interesting polynomial at all. That's p to the 12. That's a constant. Yeah. Right, so the constant term in x, which is a polynomial in y, is just a constant itself. Yeah, that's the first piece of information about this. The second is again similar. If I take this epsilon p, And I restrict it to the diagonal, meaning I set my two variables to equal to each other by the same argument essentially as before. You can show that it has leading coefficient equal to plus or minus 1. I didn't put a third point because I'm not sure what to say about that. I'm not sure if there's any kind of appetizing Kronecker congruence for these epsilon polynomials. Maybe no, I just don't know. Okay, now here, and that's sort of the main takeaway of this, the situation is a lot more pleasant than this. Now, you will still hate me for doing this, but I'll give you some examples. It's not so bad. They don't work at the same time.
You can use your hand.
You can use your hands. Oh. Just like these people. Yeah, in the spirit of the computations of these things, which are also done with bare hands, maybe I should adopt this, but this other one I can't do with bare hands. So. Yeah. I mean, the word singular really just means strange, I think. I'm not sure if moduli really corresponds to the modern way that we view the word moduli, because it stems from days long past that I was personally not a part of. But it's certainly a good explanation for the name. We know that these taus, of course, correspond to elliptic curves, and that's very quickly the viewpoint that we will switch to. So they form a moduli parameter on these elliptic curves. So on the basis of that, I think the name singular moduli could be justified. But I wasn't around. I didn't coin it, certainly. So I may be completely wrong about the intentions of whoever coined it. Does anyone know, actually, who? Yeah, singular, yeah, strange, I guess. But tau is CM, but J of tau is, that's the singular modulus. Now, because the J function, it's at sort of the J line is the moduli space. So the J of the tau is the modulus, if you will, of the elliptic curve C modulo the lattice spanned by 1 and tau. So maybe that's the reason.
So the moduli are strange because there's the elliptic curve of CM. That's why they're...
Yeah, well, I mean, that's of course the reason that they are strange, but they're algebraic, which is extremely strange. Now, if I take an apple and I put it through a blender and a banana comes out, then I'll be very surprised. And that's a little bit what's happening here, because you take an algebraic point, you take a CM point tau, you put it through this transcendental function, which completely blends it up, and out comes still an algebraic number. So that is in and of itself really a miracle. And of course, I'm starting off with this miracle, so it may all seem very natural and canonically given, but this is kind of an amazing fact. So singular is justifiable. Okay, so just to maybe conclude very quickly the classical part of the motivation. Let me give you a couple of examples. So epsilon 2, I could just tell you what that is. X plus 16 cubed minus xy. And you can now verify some of the properties that I've mentioned to you before. So that's a very nice small polynomial. I'll tell you epsilon of 3, and notice that I'm not putting any dots. So I can really tell you the full thing. The numbers don't matter a huge amount, but in case anyone wants to play around with them this afternoon, which I highly recommend, I just want to give you some examples so you have something to play around with. So 2 cubed, sorry, I'm sure you all noticed that. 3 squared, x plus 2 times y minus xy squared. Okay, and let me stop there. The next one also would fit, but already we don't really maybe care anymore at this point. But what's baffling about this is that, so these invariants here, these algebraic integers that we produce in both of these ways, they have relations between them. I'm not going to go into that, but that's really the cornerstone of the classical theory of complex multiplication, is the relation between these two modular polynomials. One being gargantuan in size, the other being quite small, but also the prime factorizations seem much more limited somehow. And it's the contrast between these two that is really of interest for the classical theory of complex multiplication. And classically, what you do is you prove that the field that's spanned out by these J invariants is the ring class field by relating these two polynomials with yet a third modular polynomial and getting it in this way. So let me just say the following before I state the theorem, which we're not that far away from it. I mean, it is a bit of work, but we're not that far removed from the arguments that will establish the main theorem, as I'll write it down in a second. So let me just note that as before, so this implies, that these H gamma of tau are algebraic when tau is a CM point. And just to reiterate what I already stated, these guys I will refer to as elliptic units. All right. So the lesson to take away is I just want you to compare the following two statements. So these are classical computations that Weber did in his book. So I'll tell you the result of this. So Weber computes in his book the J value at the square root of minus 14. Beautiful point in the upper half plane. Takes a bit to write down. Maybe I'll do that in the notes, but I'll just tell you what the norm is of this algebraic integer. Okay? The norm is 2 to the 24 times 11 to the 6 times 17 cubed times 41 cubed. Yeah, that's what the norm is. On the other hand, Weber also computes that the norm of this algebraic number is just 2 to the 24. Yeah? Where gamma here is the matrix 1, 2. Yeah? So when p is equal to 2, you have 3 choices of these gammas. And the 3 corresponding functions, h gamma, they're often called Weber functions. So you will see these in the classical literature throughout. Okay, so both of these algebraic numbers here are defined over an extension of degree 4 of Q. Yeah? It's the same extension, actually. But one, when you take its norm, has this bizarre sort of large prime factorization. The other does not. And that really reflects two fundamentally different properties that these types of invariants have. These elliptic units, they're very rigid. They're rigidly structured. Yeah? They form something called an Euler system. And that relates them to L functions. And this rigidity is sort of responsible for making the prime factorization much more restricted. Yeah? So you only see prime factors at 2, which also happens to be the determinant of that matrix. Singular moduli don't have this. They don't have this kind of rigidity to them, and it's this richness of prime factorizations that will be responsible for a lot of what I'm going to talk about in this course. Yeah? So that's sort of the main takeaway. In general, bigger is not always better, right? And so you might think if you're trying to generate extensions, you'd much rather do it with solutions of polynomials that come from this side because they'll be much smaller and more manageable than things coming from this side. But the richness here really is what is responsible for the phenomenon noticed by Gross and Zagier in particular that I will talk about. Okay? All right, so any questions before I go to a more slightly geometric viewpoint. Yes?
How many phi do we know today?
Hundreds. Yeah. So I forget a little bit about the history. So I think, 1975 was phi 7. Then I think 1984 or something, around the same time as Gross and Zagier, phi 11 was computed. Then I lost track of what happened in between. But then nowadays you look at Drew Sutherland's webpage, if you ever need a modular polynomial, which to me usually happens on occasions that I'm giving a lecture series or something on these kinds of things, then you find them into the hundreds tabulated. But of course these are computed not straight from the definition, which would take more than the length of the universe to compute. It's done by much more clever arguments. In fact, it's using the work of Gross and Zagier that is sort of the motivation for talking about this. Yeah. So into the hundreds. So we're a little bit spoiled nowadays. Another reason, so I will tell you a little bit more today, but another reason I like to give you these factorizations is that you can actually go home and try and explain why that factorization occurs based on the theory of CM elliptic curves. In fact, you have many of the ingredients already on the board. It's maybe not immediately clear how to fish out these things. So without computing the modular polynomial, I claim that you can predict what that constant term is by making variations on the statements that I've put on the board and maybe using LMFDB, something about CM elliptic curves of small discriminant, and you will be able to retrieve these. Okay, anyway, let me move on to the second part. So this was sort of the two classical elliptic units and singular moduli, and now I will move on. Let's maybe bring the middle board down to the viewpoints on Heegner points. Just to ramp up a little bit to the context, that was the context in which Gross and Zagier took place. So, of course, many of you will have realized already at this point that all we're doing really is we're describing the function field of the modular curve x naught of p with these polynomials. So we can give a sort of different viewpoint on the statements we gave, and then I'll use that viewpoint to state the main theorem of complex multiplication really for this special case of prime level that I just discussed. Okay. Right, so of course the modular polynomials that we find in the classical era they describe the cover of Riemann surfaces that is x naught of p going to x of 1. X of 1, the function field is generated by J. We have actually used that in one of our proofs. And in x naught of p by the other functions that I just mentioned. So either the MP translates of J or these H functions. Yeah, and so the picture here is that we have x naught of p going down to x of 1. And x of 1, of course, being isomorphic with the J function, defines for me an isomorphism to P1. Yeah. P1 has maybe some cusp infinity. And my x naught of p, it's something. And we have a map going down like so. So above these two cusps, above this cusp, there's precisely two cusps upstairs. In general, the map is degree p plus 1, as we see from the degree of these polynomials that appear. But there's ramification over the cusp, so you only get 2 points in the pre-image. That's the two cusps, 0 and infinity. But in general, generically, you get sort of p plus 1 points. So suppose that A now is an invertible ideal. Again, in this quadratic ring that is imaginary quadratic, then what we get is we get an associated CM point. Maybe this is not good notation, but let me call it this. So associated to such an ideal, which up to equivalence here, up to SL2Z equivalence, I just get one single point here. So I can take the CM point that's associated to this A, map it down, and that gives me a CM point here. So that's essentially the value of the J function at this ideal A. Yeah. Okay? So this is associated. Yes, sorry. So this is, sorry. It's terrible notation. But luckily we won't have to use it too much. I'll just use it in the statement that I'm about to say. So it's brackets, and then square brackets, and then a German A. That's what it is. Yeah, sorry about that. Okay, so it's associated to this elliptic curve. We could call it E of A, but I don't think I'll use this notation, which is just obtained by quotienting out by C the lattice A. Okay, now suppose we're in this situation that we saw before in action, where P is a prime that is split. So if P, I'm not assuming here principality, just that it's split, then we see that in the pre-image of this map, which consists of P plus 1 points, numerically, there's two distinguished ones. And they come from the lattices of index P that I get by multiplication by one of these two primes. I have these two sort of God-given, we get two distinguished CM points, which come from adding this level structure. And so now the notation that I will use is just with a comma and then the ideal, which will be either P or P bar, and they live inside of this fiber. Yeah, so, well, I don't know if I should put the notation here, because no one will be able to read that. But I'm writing the same expression as I do on the other board. So that's these sort of two distinguished points. Sorry. Hopefully you get the picture. All right, so these things commonly are given the following names. So this assumption here typically is referred to as the Heegner hypothesis. We can see maybe why it's natural given the explorations we did before. And then these 2 points are typically referred to as Heegner points. Everything for just level x0 of P, but you can do this with composite level as well. Okay.
Yeah, what are the basic curves and the subgroups?
Yes, so this is the elliptic curve, and then the isogeny that you get is gotten by this ideal P, which sits inside of the endomorphism ring, which is O. Yeah. So in the P torsion, you canonically have a subgroup that is killed by P and P bar, and that's the subgroup you quotient out by. Okay. I have to do this. Okay. Now, this is the type of thing that people were studying, and that's sort of the mindset that I want to put us in. when it came out that Heegner's proof of the class number 1 theorem, which is the statement that there's this list of imaginary discriminants of class number 1 that should be the full list, but the proof of that was long elusive, so it was noticed already by Gauss, by doing extensive numerical computations. And then the arguments of Heegner, as later explained by people like Stark and Birch, actually constitute a full proof. What's a bit funny is that in Heegner's work, he's working not with x naught of p, he's working with a non-split Cartan modular curves. It's a different kind of level structure, and the condition for him was that p is inert, not split. So it's a bit bizarre, but then sort of out of the explorations that later were done by Birch, this name of Heegner hypothesis and Heegner points arose. And so the following was already known since the classical work, which is a refinement really of the statements that I had on the board before, is that the Heegner points whatever the notation, terrible notation was, they're always defined over the ring class field Ko of O. And so this ring class field is defined as the one corresponding to the compact open coming from this quadratic ring O that I take, the profinite completion of, and then inside of the finite adels. That gives me a nice compact open, and the corresponding quotient is this Galois group of this mystery extension called the ring class field. So in general, the way to visualize this is we have this quadratic extension K over Q, which is imaginary quadratic, and the Galois group here which is isomorphic to that quotient, finite adels over this O hat star modulo K star, actually is just a class group of this ring O, consisting of invertible fractional ideals modulo principal ones. Okay, so it's a specific extension that you know from class field theory. This extension is the field of definition of this, and if you like, you can take the maximal order in everything I've said, and then this is just a Hilbert class field. All right, so if it's defined over this field, it might also be interesting to describe the Galois action. And this Galois action is very explicit, and this is the only time I will use my horrible notation. If I take the point that's associated to the ideal A times B, then that relates to the point associated to the ideal A with the same level structure, so with this P, by acting by the element of the Galois group that I get from the Artin symbol of B, with an inverse. So there's a specific element, in other words, of this Galois group that gets me from this guy to this guy. And that's what that element is. Okay? Okay, and then finally, I mean, that describes this part of the Galois group, but Ko over Q is also a Galois extension, and the only action we're missing is the complex conjugation. And that complex conjugation will take my ideal A and P and send it to, well, no surprise, in the second argument, now finally something is changing. P changes to P bar, and A changes to its inverse, the inverse class in the class group. So that's, these two statements are classically known as Shimura reciprocity, if you like. So we have a very good understanding of how this Galois group acts. In fact, I mean, the proof of this is quite a bit more work, of course, than anything we did today, but it's not like we're a million miles away, and you can adopt this classical viewpoint on modular polynomials. After introducing this third one, this is essentially, by proving this reciprocity law, you prove essentially all of these statements. So you can find this, for instance, in this classical book of Borel, Serre, etc., this IS notes from 1958, something like that. You find this classical viewpoint. It's quite refreshing as an alternative to many sources that you might see. Okay. Now, this is tempting, of course, because there was a time in the 60s where, sorry, I lost my eraser. Ah, here it is. Where the conjecture of Taniyama-Shimura was sort of around, and people understood that if you have a good construction of global points on modular curves, you should get a good construction of global points on all elliptic curves. And that was sort of the amazing thing at the time. So Budge, I think motivated by this, was exploring precisely this. And so let me give you one example of the types of computations that Budge was doing en masse. It was corresponding with Gross, and that's sort of the starting point of what I'm about to say. Because he was doing the following kinds of experiments. So let's do one example. So let's take the modular curve x0 of 37. Now x0 of 37 has genus 2. And so the situation can be visualized as follows. So we have our usual upper half plane, H, like before. And then we have a map where we quotient out by gamma 0 of 37 to obtain this genus 2 curve, or at least its affine part, unless I extend the upper half plane. That's what I call x0 of 37 here. And of course, x0 of 37 sits over x of 1. That's this covering described by the modular polynomials. And of course, this map is just taking the quotient by SL2Z. Okay, so that's the situation. Now, in order to give you an explicit example, what I could do is describe equations for x0 of 37 and then give you a sample of what such a computation looks like. But I'll make my life a little bit easier by passing to a further quotient whose equations are a little bit cleaner to describe. I've already hit you over the head with some modular polynomials, so I think I've filled my quota of big numbers for today. So there's a further quotient that you can take by the Atkin-Lehner operator at 37, and that happens to be an elliptic curve. It's even a very specific elliptic curve, which has the equation y squared plus y equals x cubed minus x. Yeah? That's the equation of this curve. Okay. Right, now what we could do is we could take a point tau in here. And now we could try and map it through all the way to this elliptic curve and see what kind of point we get when tau is a CM point. And I did a little experiment for you. Maybe I can fit it. Is that a good idea? Yeah, why not? So we compute the following example. So for tau, I will take the following point. And I just want to give you these numbers to show you that you can just do this yourself. And it's, in fact, it's a great way to learn this material. And I want to give you a couple of flavors of what goes into it. So the point I took for my sample computation is minus 12 plus the square root of minus 4 divided by 2 times 37. And now I have to explain to you why I took that point. Now, the first thing that I'll tell you about it is that it's equivalent to I. That's really the point I wanted to choose. If you ask me to choose a point in the upper half plane, I pick this one. Except, so this is equivalent under SL2Z, I should say, to this I. Except, of course, if I map it down here, that's my J of tau. I don't care which of the points I take, so I might as well compute it on I. And so J of tau, it's a value that you already know. That's 1728. No? Okay, except if I am interested in the image on here, I told you that there is 38 pre-images, but there's only 2 distinguished ones that I'm interested in, yeah? And this is one of them. So the distinguished ones are distinguished, if you translate it to the upper half plane, by the fact that if you write down their minimal polynomial, the first coefficient is divisible by 37, and that's the reason that a 37 appears. So you can sort of move around in the SL2Z orbit modulo gamma 0 37 orbits to find this distinguished points. And then you can try and compute what happens in this map to x naught of 37. So what I did is I just computed in this map. How is a long story, but it's fun. And if you want to try yourself, just ask me. So I'll tell you what the image P is on this elliptic curve. So what came out of the computation is that the point is 1, minus 1. You check that's a solution to this equation. But the thing that got people really enthusiastic about this kind of computation in the 60s is that this point is of infinite order. In fact, this elliptic curve over Q has rank 1, it has no torsion. And this point it's like twice a generator or something. So it's of infinite order. So that means that this construction of CM points coming from classical CM theory that mapped through to elliptic curves has a chance of actually generating, at least up to finite index, the Mordell-Weil groups of all elliptic curves. So wouldn't it be great if we could control when this happened in general? And that's precisely the question that Gross and Zagier studied. So that's the question I want to sort of maybe put on the board here. So the question is, when are these Heegner points non-torsion? You could ask, when do they generate the full Mordell-Weil group? That's the next question, but let's start with this one. When are they non-torsion? And this is precisely the question that Gross and Zagier started studying. So Gross and Zagier studied the height pairings of Heegner points. All right, so next time we will study a little bit the types of arguments that Gross and Zagier used, but I want to set the scene and I want to tell you about the beginnings of that collaboration. Now, the starting point for this work of Gross and Zagier, again, was informed by lots and lots of explicit computation. More specifically, tables of the following form. Well, in fact, let me flip it. There we go. I guess I wrote quite small. I'm sorry. But I hope you can sort of read it. Now, this really was the starting point of their explorations, was these algebraic numbers that we get, and there's still a couple on the board of these singular moduli. They tend to be very rich and have lots of rich prime factorizations, like the constant terms of the modular polynomials, these kinds of factorizations, and the ones that are here on the board. In fact, this kind of table you can find in the literature, and there's a paper of Burrick, the same guy who computed phi 3, I think, by hand. He had lots of tables of singular moduli, and he was interested in the factorization of j of tau, and j of tau minus 1728. So these were the two quantities that he was studying. He was making lots and lots of tables, and then making lots of observations and conjectures about what the types of factorizations are that you might find there. Maybe I'll give you a minute to stare at it and form your own conjectures. So Burrick's paper has maybe like 15 different conjectures, most of which are correct. Some of are incorrect, but that's just because he was computing by hand and he only had very limited data. But there's a lot of correct ones. And so maybe one thing that's kind of striking, and that's the one I thought we could zoom in on next time to explore the arguments of Gross and Zagier in this very kind of concrete way, is there's a striking power of 2 in some of these entries. So minus 11 and minus 19, for instance. There's a 2 to the 15th in the factorization of the singular modulus. By the way, all of these are class number 1 discriminants. So the J invariants are algebraic numbers of degree 1 over Q, so they're integers. That's also why I left out minus 15 and minus 16. Or well, at least minus 15 has class number 2. So this 2 to the 15 is quite striking, and that's something that Burrick conjectured in his work, and that's what I want to start off with next time. But let me just, so now I would like to maybe finish by telling you a story. Well, in fact, I'll let Gross tell a story. So just to get us motivated for the arguments to come, there's a nice paper that Dick Gross wrote about his recollections of the early days of this collaboration with Zagier. And so essentially what happened is that these kinds of computations, which Birch was doing, led to lots of sort of precise conjectures that Gross was making, their correspondence is also published, about relationship between Rankin-L series and derivatives of Rankin-L series and heights of Heegner points. And so Gross had all these kinds of conjectures, but there was the real expert, so Gross writes in his notes on Rankin-L functions, was Don Zagier. So he started talking with Don Zagier, and there's a whole letter recounting the origins of this story. I won't read all of it, but I'll read a sort of a section of it. And the setup is that at this stage, they were trying to compute these expressions of derivatives of Rankin-L series, and all kinds of explicit expressions showed up, including these mystery integers m. And Zagier sort of asked to Gross, according to the letter, so Don pointed to the sum and asked me in an exasperated manner what the integers m were supposed to be. And then essentially, Gross says that he guessed that they were related to the powers of p for prime p of the j function and the j function minus 1728. So this was sort of a wild guess that Gross made, that these integers should be the exponents arising in these factorizations that I have in this table here. So that was Gross's guess. And so then Gross writes, this all seemed far-fetched, as nothing in Don's computation suggested any relation with singular moduli. But at least it was something that we could check. The algebraic integers, j of tau, had been computed for discriminants with small class numbers and were tabulated in the literature. Since by then it was 3 o'clock in the morning, I suggested that we go to sleep and look up these values in the math library the next morning. There were no tables on the internet in 1982. If my guess turned out to be hopelessly off the mark, we could bring this nonsense to a stop. After these somewhat dispiriting remarks, I went to bed. I should have stayed up. Although Don was completely exhausted and had only a small handheld computer, he set about calculating as many singular moduli as he could, and in each case checking my guess. I woke up to find his living room covered with paper. It took me a while to figure out what was going on. At the top of each page was a discriminant. This was followed by a calculation of its singular moduli. At the bottom of each page was a check mark indicating that the powers of p in their factorization matched Don's formula exactly. The last page was in large print and said, "Wake me up immediately," which I did. That morning we were both in a state of mathematical euphoria. We knew that we were onto something important. So that night we went to a faculty dinner and sat with Steve Kudla. Don excitedly recounted his computation, and we asked Steve if he had ever seen sums of the form RA times RB, which involved the product of representation numbers of two binary quadratic forms of the same discriminant. Steve remarked that these were the representation numbers of the sum A plus B of the two forms, which is a quadratic form in 4 variables with square discriminant, the norm form on a quaternion algebra. I knew very little about quaternion algebras at the time, but I did know that the endomorphism ring of a supersingular elliptic curve is a maximal order in the rational quaternion algebra ramified at infinity and p. Writing its norm form as the sum of two binary forms of the same discriminant is equivalent to embedding a quadratic order into the quaternion order. So that's a little bit the viewpoint that we will adopt tomorrow. So to finish, I will write down 2 concrete statements. And another reason for reading this quote is that if you don't know what a quaternion algebra is, you're in good company. That's number 1. But like Gross, you can now go home and learn what they are, and then tomorrow we can do some computations in quaternion algebras to try and explore algebraic proofs of the following statements that we might notice from the table. So the first which was discovered experimentally by Burrick. This is a conjecture. (1927). We can sort of get by staring at this table. Burrick had much more data. So suppose that we have a negative discriminant. I won't repeat that, but its absolute value is 3 mod 8. So the discriminant is 5 mod 8. If this is true, then 2 to the 15 ought to divide j of tau delta. Yeah? We already noticed this one as well. There's a second statement, which I don't know yet if we'll talk about it tomorrow, but j of tau. Yeah, I'll say something about that in a second. So if it's 1 mod 3, then just to use the right column as well, 3 to the 6 should divide j of tau delta minus 1728. No, I mean the j function. So the j function will be defined in some extension. And what I'm saying is that for every prime that you pick above 2, the 15th power will divide it. So it's really, yeah, I mean in that field. That's the statement. Here, of course, there isn't really a difference because everything was class number 1. But in general, that's the statement. And in fact, I'll insist on that because tomorrow I will prove a sort of also a converse maybe of this, that 15 is the optimal power. You can't go bigger than that. Now, why do I mention this? It seems like a curiosity, which maybe at one point it was, until Gross and Zagier put their hands on it, because it involves the type of argument that Gross and Zagier make in their paper. Now, the statement that they prove is much more involved, and I'll give you the statement also, but I think maybe instead of sketching the proof of that particular formula, it's more instructive to focus on this kind of simpler case, which involves really all of the same ideas of Gross and Zagier that led them to the proof of their formula. So it's sort of a bite-sized version of their big theorem, which is the following. Yeah, and so it's the first paper that Gross and Zagier wrote together, which is called On Singular Moduli, which contains already many of the germs of the ideas that go into their big paper, and it gives us a good way into this material, I think. It's quite concrete. And the statement is the following. So fortunately, the whole correspondence is very well documented. So I read you this letter, but there are some other letters also of 1983 of Zagier to de Gross, where he essentially explains that their observations on j of tau and j of tau minus 1728 could be generalized to differences of arbitrary singular moduli. Because j of tau you can regard as j of tau minus 0, 0 being the singular modulus of the 6th root of unity. And of course, j of tau minus 1728. 1728 is the j invariant of I, which we already had on the board. So they're both instances of differences of singular moduli, and that's a little bit what this work evolved into. So the statement is the following. So suppose that we have delta 1 and delta 2 fundamental discriminants that are coprime. Then what I can do is I can take j tau 1 for any CM point of this discriminant delta 1 and subtract j tau 2. That's a big algebraic number in the compositum of the two Hilbert class fields by the theorem that I think is still somewhere on the board. And if I take its norm down to Q, because this thing in brackets is an algebraic integer, I get an honest integer out. And that integer is essentially given by a completely explicit formula. And what exactly the formula is maybe doesn't matter all that much, but I'll give it to you anyways. So the formula is the following. So there's 3 quantities appearing here that I have to define for you. So the product here is over x squared plus 4mn, where m and n are positive integers. X does not need to be. Such that x squared plus 4mn is equal to delta 1, delta 2. No? Okay. Delta 1, delta 2 is, of course, a positive number. So I can see that this product is a finite product, because m and n are positive, and x squared certainly is. Okay, so that's what m and n are, where epsilon, it's a certain character, if you will. I'll define it for you on prime values. And then I extend multiplicatively to all composite values, and that's what epsilon m is. And it's defined to be the following. It's defined to be this Kronecker symbol, delta 1 over p, if p does not divide delta 1. And the other one, if p does not divide delta 2. And of course, because delta 1 and delta 2 are co-prime, one of the two cases at least must happen. And you can also check that for anything appearing in here, the two values will agree, which is not a priori clear. Okay? And I think that's the formula. Now I just have to put some bits and bobs. This is up to a sign, and I have to raise to some power, which is 8 over W1, W2, where Wi is just the size of the unit group in the ring of integers of the quadratic field spanned by tau 1 and tau 2 respectively. So that's kind of the formula. Okay? So next time we will sort of study the ideas that go into this by applying them to this simpler setup here, but I think it contains all the germs of the algebraic part of the argument. And then we will focus after that on the analytic part of the argument, which is really the one that will set us up to explore what might be considered some instances of the p-adic Kudla program. Okay, so with that said, tomorrow we'll continue. We'll go into the work of Gross and Zagier, and also tell you a little bit about RM singular moduli, or at least some of the prerequisites for that. The audience is very diverse, so there's many master students all the way up to some senior people. So if this is new to you, then use the opportunity also this afternoon, puzzle these things out. I gave all of these explicit numbers for a reason. It's a subject that lends itself excellently to just getting your hands on it. And I think that's really the best way to absorb it if you haven't seen this kind of material before. Try and engage in an explicit manner with all of these objects. They are really excellently suited for this purpose. And if you get stuck, just ask someone or ask me. I'm also around this afternoon. And tomorrow we will continue the story. So thanks very much.